Good afternoon, everybody. And this is a APSIPA distant quiz lecture. And my name is Professor Ambikairajah. I'm a head of School of Electrical Engineering Telecommunication at UNSW, Australia. The title of the talk is Speaker Verification and looking at the present and the future voiceprint based security. So this is a 1 hour lecture, around 1 hour, so I can only give you introduction and also I'll give you directions for future. Later on we will be recording advanced lectures for you as well. So let me just, without any delay, I just want to thank the Ho Chi Minh City University Technology Vietnam for inviting me to give this APSIPA distinguished lecture, and thank you again for the invitation. First, we look at APSIPA. APSIPA is the Asia Pacific Signal and Information Processing Association. It's a very young association. It was founded in 2009, and APSIPA committee every year select about 4 or 5 lecturers. They are called distinguished lecturers. They are expert in their signal processing, information processing area, and they normally give 1 or 2 lectures in various places, and they've been selected to give lectures. So the idea behind the APSIPA Distinguished Lecturer Program is to serve its communities by organizing lectures. This is one of the lectures which I am giving, and also we promote the research and in the area of signal and information processing in the Asia Pacific region. And APSIPA Distinguished Lecturers they are actually an ambassadors for APSIPA, for promoting APSIPA's image and reach out for new membership. So you will see, if you log into this site, you will see all the APSIPA lectures that have been provided by various experts in this area over the last 5 years. Now, this introductory lecture which I am giving, and I'm hoping that some of you will become as members, or all of you become as member of the APSIPA, and then once you finish your PhD, or those who have already done PhD working in this area, will eventually become as an APSIPA distinguished lecturer and give lectures for the future students. And so this cycle continues. So I encourage you all to become as members. There are various memberships available. You can look at it on the APSIPA website. So just look at the outline of this particular talk. So I just give you about introduction about speaker verification and speaker verification application. Where are the applications? We have a simple verification system. I will show you and how to implement a simple system, and then I'll show you the trend of what's happening currently, and also give you direction for the future. And how do you do it in a simple system? How do you do the performance measure? And the NIST speaker recognition task as well. I'll talk about a little bit on that, and then give a discussion, so we'll have time to have a lot of questions to discuss. So the introduction is basically, what can you infer from speech? So here's a speech wave, or if you are speaking to somebody from a telephone conversation, what can you infer? From a speech we can say what's being said, definitely we can say. We can also say the language being spoken. So if you know 3 languages, if what the speaker says falls within 3, you will identify any one of the 3. Otherwise, you will say, well, it doesn't belong to these 3. Okay? You can also, if you know the person for a long time, speaking to him, without seeing one-to-one through the speech, you can say who is speaking. You can also say the gender of the speaker, most of the time, whether it's a male, female, child, reasonably accurately. Age of the speaker also is possible. Age means not exact age, whether the person is a mid-age or over 50, 55, 60. Roughly you could say which band they fall in, rather than exact age. Emotion. From the speech you can say, yes, this person is happy, or this person is sad, or this person excited, or a person is bored, or slightly depressed. All sort of things you can actually infer from the speech, emotion. And the stress level, is the person stressed out, because if you take a telephone operator answering 5 phone calls, one after another quickly, well, will be a person with a very high cognitive load, because the mind is working. So that's the next part. Whether it's a stressed out or very high cognitive load, you can say from the speech. The depression level also, you can roughly say whether the person is very highly depressed or not. You can make a classification of depressed against not depressed. If the person is sleepy, you can say, if a person is inebriated, also you can say, So these are, from a speech, you can roughly say. And I'm not saying you can say accurately, but these are the things that we can actually infer from speech. So if you look at a person speaking, that's our transmitter. And that's our receiver. Person listening is our receiver. And that's the speech. And assuming, we have this conversation either one-to-one or from a telephone. And from the speech, we can say what being said. So we can say, the person says, how are you? We can use a speech recognition system. The brain acts as a speech recognition system and say, yes, how are you, is what's said. Also, from the speech, you can say what language was spoken. So it could be English or non-English. So that's called linguistic information. And paralinguistic mean, because recognize the speaker. We could say, the person on the other end is me. We could say that because we know we have recorded the person's pattern, talking to him many, many times. Your brain recorded that, so the next time when the person speaks to you, you're able to recognize the speaker. And emotion, if that's this person, whether the person is happy or sad, you can say from the speech. And also you can say about the cognitive load, so the person is very highly loaded mentally or not as well. So this part, we call this as a linguistic information. We call this one as a paralinguistic information. This is from speech. You can actually say all of these things. So in this particular case, what we are going to look at is only speaker recognition. We are not looking at this. We are not looking at that. Not that, not that. So for this talk, we'll be looking at speaker recognition. Speaker recognition, if you take, there's 3 parts we have. One is speaker identification. So speaker identification determines who is the speaker from a set of enrolled speaker. So you have an unknown person coming in. We've got many models stored. We check this person against this one. That's speaker identification. Speaker verification determines if the unknown voice is from the claimed speaker. A person says, I'm John, so you check against John's data and then make a decision whether you accept John or not accept. That's called speaker verification. This is checking it against many people. This is checking against the claimed person. Then speaker diarization is partitioning an input audio stream into speaker 1, speaker 5, speaker 3, speaker 2. So you can actually segment them into various speakers. So that's called speaker diarization, and it is done according to speaker's identity. Now let's look at the next slide. Now we have speaker identification, just to give as a simple example there. And what we do, we create a model for each speaker. So bank of models there. So speaker 1 model, speaker 2 model, speaker M model. Unknown speaker speech is coming through. And we check, we extract features from that and check against this model. And you then say, well, this one matches to best matching speaker. Whichever the best matching, you say that, unknown is equal to speaker 2, for example. In the speaker verification, the person actually claiming as one of the speakers, the person claims, well, I am speaker 2 only. Here's nobody's claiming anything. You've got to check against every one of them and see the best match. Here, person is claiming against 1. So he says, I am speaker 2. So you take this information, the speech, and analyze it and extract features from it. We'll come back to that in a minute. And then check against this model only. And then if it is within a limit of a threshold, you say, yes, I'll accept the person. If not, you say, I'm rejecting the person. He's not the claimed person. So this is only checking against one. Speaker diarization is, you've got a speech pattern, you go and search through and say, that part belongs to speaker 1, and then that part belongs to speaker 2, and so on, and this speaker 1 again. So they are the 3 things that I was talking about earlier. We will concentrate on speaker verification. Okay. So speaker verification application. What are the applications? So for example, in this case, we have got an application where access control. So we got application, here we need to have access control. So in this application, a person is supposed to, let me have a look.
Artificial intelligence is for real.
This person actually talks using his voiceprint. The system recognizes and it opens the door for the person to go in. That's for access control, we use that. Now, this is for authentication. Authentication could be for bank transaction. So this is another example. We took it from YouTube, actually, this example. A telephone credit card purchase, and for the transaction, they do this one. So let's have a look at this. Let me increase the volume. It's already 100%.
Check credit card balance. My voice is my password. Awesome.
2 tickets to see James Rush tonight. My voice is my password.
In this example, the person says, my voice is my password. That's all the speeches is. And system identifies, yes, that's the, verifies, yes, that's the person, and give the transaction, the person continues to do the transaction. So people can have this access through their normal mobile phone, and that's an example they're showing for 2 people who are doing transaction. It could be a bank transaction, it could be any transaction. So speaker verification will be, part of your mobile phone. Already there are applications in the mobile. Now in the future, it will be used in mobile phone all the time. We look at a basic system. Now this is the basic system that we are looking at. Those who have never done speaker verification, some of the students who are here and who are now in the final year or in the PhD, you're trying to learn speaker verification, try to implement a system. Try to think a basic system first, implement that, understand that one first. Once you've understood that, then you go on to the next system and so on, and improve the system's performance by implementing in the state-of-the-art system. So we look at the basic system in the basic overview. Always in a speaker verification system, you will have a feature extraction block, which we call as a front end. And then we have a back end. In the back end, we will have a speaker model. I explained to you earlier how to create a model. We'll come back to that in a minute. You have a speaker model, and then you compare what comes from here to the speaker model, and then you do classification. You classify whether it's correct or wrong, and then you make a decision. Once you know the classification score, whatever comes out, you then make a decision based on it. Yes, I'll accept the person who claimed to be the speaker, or I don't accept this, reject. Right? So the previous example for the opening the door and the close the door, and the system may accept or may not accept. So it's purely for security application. You can use that sort of a. So the front end converts the speech signal into more convenient representation, typically set of features, because these are time samples. You can't use directly the time samples. A lot of redundant information is in here. We don't need that information. So we need to extract certain features, and if you use directly, then all sort of problem you will face, which we can explain that later on. So the back end compares the representation of the model. So the model provides the representation. Claim speakers here, speech is analyzed. Then we do a comparison here. Once we have done the comparison, we make a decision and then classify. So we tend to find how well this representation, well, this speech after transformation, the features are represented, how well it's giving a best match. So any speaker verification system will have a front end and a back end. Okay? And the complexity comes in here. Here, how do you get the feature extraction? Then how do you get the speaker model? And then why complexity comes into play? Because when you are creating a model, you may be recording speech on using a normal phone. But when the person is claiming, the person will be using a mobile phone, or maybe using a phone in a shopping center. So the channel variation, all sort of variations there. So we need to look at how do you create this model and to remove all these variations. So that's where the complexity of the system comes in. If you are implementing a system in a very quiet environment, like in a room, inside an office, then the system is very basic. You don't need complexity. Apart from variation from the speaker, from time to time, you need to consider that. So what is speaker verification system? How do I do it? Okay. So here's a person says, I am John. Okay. We take this speech. That's time samples here, time versus amplitude here. We pass it through a feature extraction model, which gives us something like features from C0 to Cn. And the features may be done as frame by frame basis. We just frame them like that, and it could be 10 millisecond or 15 millisecond. The vocal track changes every 10 to 15 millisecond. We could have an overlapping frame or non-overlapping frame, but for the moment, just say frame by frame, we get features here. And what we then do is that we have a universal background model, which we create using lots of speakers. We create a one big model. Then we create a model for speakers who want to verify themselves. So in this case, John, he said, I am John. So we go and take John's model, and here is the features. We feed the John's model here and see what level of match we have, and work out what's the likelihood is going to be John. Well, likelihood is high, find out the likelihood. Then, with the same John, determine the match level for the background model, and they say, what's the likelihood of this person? This is a male or female. In this case, it's claimed as male, so what's the likelihood of generic male? Then find the likelihood ratio between that and that. So likelihood ratio decision making. And if the likelihood, it's a highly likelihood, if the ratio is good and high and good match, then we accept them. You need to create a threshold and say, yeah, well, if it's below, I'm going to reject. And rejection depends on application. We'll come back to that. So here the system says, no, the match is not good, I'm rejecting. So if you look at in this case, there are three major things that you need to do. What are the three major things that you need to do? Is before you do even implement a system, that you need to make sure that you're going to develop three things. What are the three things? Okay, let me run through this one. This is a system. First, you must generate this model. You need lots of speech data recorded from various people, various handsets. You need to develop this one, which is called universal background model. Then we are going to develop this model for each speaker who is registered as a speaker, and we need to develop this model. Then we need to have a feature extraction. Right? But this is already there because this is required to develop that. This is also required to develop that as well, which I haven't shown in the block diagram. Then for the unknown speech, this feeds in here, do the ratio. So all these need to be done beforehand, before you implement the system. Okay? So UBM represents the general speaker independent model. So it doesn't depend on any speaker, but you could have two models here. One is male model, one is female model. You can separate them. And then it's compared against the person-specific model. This is the person-specific model, John's model. compare again the generic model and the decisions made as accept or reject. You will find that this model is derived from here. And we'll come back to that later on. Okay? So that's your simple system. How do you calculate all of these? Is simple mathematics available. We can look at them later on. Now speaker verification system and speaker enrollment. Now we're going to enroll the speaker. What are we going to do? We are going to create a UBM. So we have speaker 1's data, speaker 2 data, speaker 3 data, speaker N data. We create a background male speaker data. So massive data. This could be hours and hours of data of various speakers. They are not specific speakers. They are not part of this one. They are part of the testing system. These are just speakers randomly, 5,000 speakers, 2,000 speakers. We extract features from each and every one. So speaker 1, we frame it and we extract features. And we do a model training using that speaker, followed by, like all of them, all the speakers, one after another, we do a model training. Now, there are in between few things there. I'm not going through the detail, but you think it this way: for that many speakers, we extract features and do a model training and create a model which is called male model. And then if you've got female speakers, then do that generic female model. That's your first step. Now, what algorithm you use for modeling and all thing, we'll come back in the advanced course. Once we have done that, then you've got a universal background model. Now these are the specific speakers. These are the target male speakers I have. These are the speakers need to be verified. So, well, later on when they give the test data. So I take speaker X1, I extract feature from that and use this model to use this speaker model and adapt, make changes to this model to get this one fitted in. So I get a model adaptation, I get a speaker 1. So you say, this is my universal model, here's a new speaker. I say, well, if I adapt this slightly change, I can get this guy in. So the parameters belong to this is modified to get the next one. And similarly, for the next speaker, I use again that one here, and model adaptation, I get the model for that person. Why do you do this way? Why can't you do like everyone individually without using the... You can do that, but the problem is, if you want to do that, you need to have hours and hours of recording of that person to represent that. But it's very difficult. So you do independently a model, which is called a background model, and then you adapt the model, change the parameters to get the actual person's model. That's what we are trying to do. This is a very good technique to avoid recording for everybody. A lot of recording. You still have to record, but not lots of recording. So detailed speaker verification system. So you probably won't see this way, but I thought it might be better to put a detailed system. So if you look at a detailed system, you've got a speech, feature extraction. And after feature extraction, you will have feature normalization. Now you'll ask the question. So many years ago, like a lot of people spend a lot of time on speaker normalization. One is Kepstrel mean subtraction. And why you need to do? Well, you are recording the person's speech using one particular microphone. Then you are recording, testing the person with another set of microphone, not the same microphone, because the person is somewhere else. So you will have channel effects, changes, because one uses a channel of telephone cables, the other one uses some wireless and telephone. So in that case, you need to do normalization using that technique. There's another technique called raster. You can use them. You can do some sort of a feature warping technique, warp them to a Gaussian distribution. Feature mapping is also another way of feature normalization. So people have spent a lot of time in these 4 techniques for feature normalization. And a lot of people tend to do feature warping nowadays. You can do others as well. Very, very effective, which time consuming, but it's effective. And you can learn all these yourself, looking at and see what are the difference from each and every one of them. Later on in the advanced course you will see. And once you have done that, we do the speaker modeling. So you did the speaker modeling, as I said earlier, I showed you previous slides, and you do speaker modeling. So you have done the speaker modeling. If I go back, and these are the speaker models. You have done this one using this universal background model. Once you have done the speaker model, then you do model normalization. Because the model normalization, one, that whatever after modeling, your model, your system would have speaker effect and channel effects. And we need to do a normalization, model normalization, so that we think it this way, a simple way of explaining. If the speaker effects and channel effects are nearly in phase like this, if you can find a transformation which can rotate these two in 90 degrees, you can extract speaker effects. That's all you want. You don't want the channel effect, because you are trying to verify the speaker. So this normalization is a transform which is actually using one of the technique is NAP, another one is joint factor analysis. Most recently I vector, because I vector gives you a reduced dimensionality. And then within class normalization you have to do. You do linear discriminant analysis. Most recently, since 2010, is PLDA, probabilistic linear discriminant analysis. And this is what currently people are using. You need to understand all of these techniques, because the data here, like after speaker modeling, you'll have massive data, because you are going to model it using Gaussian mixtures, and you're going to have a lot of dimensions very high, and you want to compress the dimension, as you want to reduce the dimension. If you want to reduce at the same time, you want to make sure speaker effect, channel effects are in two different directions, so you need to do some sort of transform. Yeah. So people have been working on this area for a long time. And after model normalization, you classification and scoring. That's what you do normally. Score normalization is required as well. Why do you do score normalization? If you have got two systems, two speaker verification system, and you want to fuse them, you want to use some part of this to make a decision. So when you have two systems, speaker verification system, the output could be different ranges. It's like when you do your degree, you've got your final year marks is between 0 and 100, or the overall average, or for another degree your average is between based on GPA, which is between maximum 4. In that case, two different ranges, but the system is same attributes they have, same graduate attributes. The degree provides them two same degrees, but different ways of output is different ranges and different ways of interpret. So you need to normalize these two outputs to they come in the same range before you pull them together. Okay, it's a small transformation. So there are zero normalization and test normalization, T normalization available technique, and then this is for multiple systems. You have got many speaker verification systems. You can combine them, use all the knowledge of all of them, and combine them, and then you make a decision. If you have a simple, only one system, you probably may not need this at all. We've got multiple systems. So one system, two system, three system, then you need to combine that. So what this is giving you now is the detailed blocks of what you need to know. So if you are going to get involved in speaker verification, you have to start and think, well, let me understand what is feature extraction. First, well, I've understood feature extraction. Then you have to start to think, well, I need to do normalization, feature normalization. What is feature normalization? What are the techniques available? How do I do it? So you need to learn that. Once you're done the speaker modeling, well, I need to model them. How do I model them? Okay, you learn that one. When you do the modeling, then you need to do model normalization because the modeled output will be very high dimension, and also it has got speaker and channel effects still in there. Even though we have done some bit here, still it will be there. You want to find a transform to rotate them, two separate things, and you need to do some of this modeling technique you need to learn. And then you need to understand how do you do classification, whether you do scoring or whether you do SVM, support vector machine classifier, or you do sparse representation classifier. You've got to work out score normalization. If you're going to fuse a system, you need to understand that, and then your decision making. So quite a bit you need to learn if you are learning very first time. If you want to get a good system, a very robust system. If you want a basic system, you can avoid some of these, but it's basic. The error rate will be high, yeah? So what we're going to do now is, excuse me, we're going to concentrate on the, sorry, let me put this in there. We're going to now concentrate only on the feature extraction. So I'm going to just explain to you what is feature extraction in a simple form, and then you can learn detail later. You take a speech waveform. Here's a speech waveform coming in, and I take a frame one. The frames are normally overlapped, but in this case I'm just using non-overlapping frame just to make sure that for simplicity I'm using. So you take speech and then you do a windowing. Windowing could be a hanging window. So speech waveform is windowed. And then you take feature extraction, extract feature using Fourier transform, and then the known one is a Mel-Kapsel coefficient, but you need to learn how to do it. And then you got a feature vector of that much, n vectors. So if you take this one, 25 millisecond, so if you take 8 kilohertz sampling rate, 125 microseconds the sampling period, microsecond. If you have 10 millisecond, it will be 125 sample. It will have 20 millisecond, 250 samples, and it's more than 250 samples in here. But this might be only 13 coefficients. So you have already done a time to frequency reduction there. Time samples have been converted into in a kind of a spectral information there. And then you do the second one as well. Second vector. That's the second vector for the next frame, and the next frame, and the next frame, next frame. I'm just assuming n frames. So you got, for this much of samples, you got 13 coefficient. N, I put n there. And then you have another 13 coefficient. Another 13 coefficient, another 13 coefficient, another 13 coefficient. If you got 100 frames, you got 100 times 13 coefficients. So time samples have been transferred into features now. Now the next thing is feature normalization. Remember, I just show you one normalization technique. So what I have is, what I'll do is I'll take the first coefficient of this, and the first coefficient of that, C0, and the first coefficient of this, and the first coefficient of that. That's called coefficient 0. And find its distribution. When I find its distribution, this is the distribution. My distribution shows C0 distribution is something like that. I want to normalize it like such that it looks like Gaussian. So everything could be normalized to one particular distribution. So I use a feature normalization technique. And so by doing feature normalization, that is normalized, I get a normalized coefficient. That, all the coefficients are normalized, I get a normalized coefficient, and so on, so on, so on. You normalize C0 first, then C1, and C2, C3, and Cn. Right? And then if you go and pick up the C0 only, and find the distribution, if it's normalized distribution, it will be like a Gaussian there. So you are removing some sort of a variation. The channel effects can be taken out here. So that's how you do feature normalization. Just a simple example of a feature normalization. So a distribution change you are doing from that distribution to that distribution. So all the coefficients are, if you plot all the coefficients, like frame 1, frame 2, frame 3, C naught will be there, the value could vary. I'm just they're not always positive. Well, C naught is always positive. C1, C2 won't be positive always. So that's an example of a feature, extract the feature and then normalize them, okay? Then I have normalized coefficient for frame 1, frame 2 and frame P. So that's speech waveform, like if you have got a speech waveform like that, that's my frame 1, frame 2, frame 3. Remember they overlap, but in this case I'm drawing without overlapping. You can say, well, I have got coefficient belongs to this C naught and the C naught and a C naught and so on. If I now say, like, what is the variation from there to there? How, if C naught, if you plot the C naught, it varies like that. That's first value, second value. I will be interested in the slope. And this slope, next value. So variation between that, and the next one, and so on, C naught, that's what we call temporal derivative. Temporal means frame to frame we are looking at. This is a frame 1, frame 2. The C naught variation in frame 1 to frame 2. That's called temporal. That's we call delta vectors. So I get D naught, D1 because I subtract them, or different ways of doing it, right? You will learn that later on. So you do temporal derivative. And then say after this, you would like to know the variation between this to this, again, second time. That's another temporal derivative you do. So you started with 13 coefficients, for example. You derived another 30, that's this 30, and you derived another 13, another 30. So you will find for the one frame alone, you need that many coefficients are represented, 39 coefficients. So frame 1 features are 39 dimension. That's the first one. The second set, the derived one and a derived one. So a frame of 25 millisecond time samples being represented by a 39 dimension of features. You can have more than that as well, but just example 39 normally used. So that's your front-end feature extraction. These are all after feature walk. So now we come back again, right? We have done the feature extraction and the kind of normalization. We kind of concentrate on the modeling a little bit. Let's have a look. Okay, now we look at speaker modeling. So let's look at two clusters in feature space. So there are two clusters here that could belong to the same speaker, and we plot, for an example, C naught against C1 is a two-dimensional, and the probability distribution for cluster 1 looks like this, and for cluster 2 is like that. So if there are for one particular speaker, there may be many clusters, and so we will see the probability density function like this. Maybe another, in the feature space you would have another one, so we've got third one and a fourth one. So how do we model this probability distribution? That's the next part. So we know in a feature space these clusters can be kind of represented by, modeled by probability distribution, and then if that's the case, then how do we do the actual modeling? What do we need to do? So here's an example here. You can see in this example, it's a one-dimensional example. The black curve that you have is the overall PDF of one particular speaker, for example, right? So if the black curve is the overall PDF, how do you model this? So what we need to do in this example is we have got a Gaussian mixture 1 and a Gaussian mixture 2, Gaussian mixture 3. By having three mixtures, 1, 2, 3, we are able to roughly model the black PDF, overall PDF. And one Gaussian, so if you take this Gaussian, it has got a mean, and it has got a variance, and also it has got a height. So there are three parameters required for a Gaussian to be represented. So this PDF, this probability distributive function, can be modeled by a mean, and a variance, and the height, which is the weight we call it. In this case, we have to make sure in the three, all weights must sum to 1. So we got to, when we are modeling it, so that weight, that height plus that height should sum to 1. So that's how you model it. So what we have shown here is an example of a one-dimensional probability density function, and probability density function approximated by 3 component of Gaussian mixture model in this case. And each Gaussian mixtures consists of a mean and a covariance or variance and the weight. So that's how we do a model of just a simple example I've shown you as speaker modeling. This is for one particular speaker, you could say, right? So let's go to the next slide and what exactly you do. So in order to, let me go back again. Yep. In order to do the modeling, we need to have, database. So database for creating a UBM, universal background model. How do we create the database? So we need a training set to create the UBM. So in this particular example that I have used, I had 56 male speakers. Each speaker consists of 2 minutes of active speech for creating the UBM. So that's the data I use for creating the UBM. Once I have created the UBM, then I have to use a target set to create the speaker model. So if there are 20 speakers involved, and I have to create a model for each speaker, and this model is created from the UBM. So you must create this first. Once you have done that, from that you can create a speaker model. For this speaker model also, you need a data. So each speaker consists of 2 minutes of active speech for speaker specific model. So there's 2 different data. This is the second data, which is called the target test, or sometimes called development set. Then once you have got these 2 models done, then you need to have test set to evaluate the performance. So you need to have another set of data, which is the third set of data here, which we have in this case 250 male utterances and with known identity. So these 200 male utterances belongs to these 20 speakers' identity. Okay. So once you have set up this one and this one, the models, then you do testing. And the database is like, we divide them into 3 sets, as I did before. This is another way of a bit more detail in it. So we have a background set, which is the set that you create UBM and also create models for imposter models and score normalization. We need later on, you will see that we can use some of this data. And then we have the development test, which is we got the target one. And this is to make sure that using the development set, you can tune the parameter of individual speaker model. So that is that one. And the third one is the test set, or we call the evaluation set. And it's an independent evaluation database that is used to evaluate the final systems, and that was optimized on the development set. Once you have optimized your development set for each speaker, once you have got that, then you do the evaluation. Okay? So what I've said earlier is just a bit more detail here given to you. Now, from the UBM, what do we do? How do we get the speaker model? We looked at this before. So let's say that we've got for one particular speaker, we saw earlier 2 clusters. Now in this case, we say there are 1024 mixtures, around 1024 clusters, or around overlapping clusters. So we got 1024 mixtures. So universal background model that we are going to create using the training set is 1024 mixtures. And for this one particular cluster 998, I've shown you an example. It will have a mean, and it has got a covariance and a weight of 0.2. Similarly, every mixture would have that. Now, in this particular feature space, I now plot the target speaker. You can see the target speaker, this particular, I'm trying to create a speaker model. So target speaker, when you plot them, they're just away from this particular mixture. This mixture belongs to that, and this target speaker is away from there. And this cluster is also for target speakers away from that. And the another one is just within that. So we don't need to do anything for that. In this case, what we need to do is we need to use the mean and the variance and the weight. We need to adapt them to get another set of 3 parameters, another mean, new covariance, new weight. Similarly, from this mean and covariance and weight, we adapt them to get new set for the target speaker. So once we have done that, for example, this example I'm just showing here, and here look, I have done the adaptation from UBM. I create a target model for one particular speaker using the UBM. UBM is these ones, yeah, these distributions one. Now you can see now I moved from this one to this one for my target model, and that particular model, if you analyze them, from here I did it, and the mean was adapted. I got a new mean of 0.8, and the weight covariance was adapted, and I got a covariance of 0.5, and the weight was adapted as well. I got a higher height here is 0.3. So that's how you get from your UBM, you adapt the UBM to get a speaker model for each speaker. So this is for one speaker, and then you do, but this is an example on 2 dimensions. But so target speaker model also consists of 1024 Gaussian mixtures. Why do we need 1024? You could have 512. But the feature space modeling, you know, trying out many times, people found that 1024, 2048 mixtures actually models them very well, feature space. So this is how you actually adapt. So the adaptation algorithm is expectation maximization algorithm. We are not going to go through the detail, but you use that one. So remember, we have a UBM. So UBM, we have already found all the clusters, all the parameters, and from that you get speaker model 1, speaker model 2, and so on. So how do you represent the UBM now? Just look at the UBM. How do you represent? What sort of dimensionality they are data-wise? So represent the UBM. Let's say I just take for an example. Sorry, I didn't say UBM. It's a Gaussian mixture model. Okay, how do you represent? In this case, the speaker that we are interested in is speaker 1. We adapted the speaker from UBM to using the expectation maximization algorithm for UBM to, and we got speaker model 1. What does that consist of? What sort of parameters we have? So we start with the speaker 1x1, and speaker 1 has got 1 mixture, 2 mixtures, Gaussian mixture, and 1024. That's what I mentioned earlier in the previous slides. Each mixture consists of a weight and 39 features we have. So 39 means and 39 by 1 covariance. That's each mixture. So when you have 1024 mixture, you will then form the whole lot together as a vector, and you've got a weight vector and a means vector and also covariance vector. This is what the GMM, Gaussian mixture model representation for one speaker, that's speaker 1. You have to repeat this again from the UBM for the speaker 2. So you got to adapt the UBM to get speaker 2 representation, and then that's for second speaker. This is how you create the speaker model. So from UBM, you adapt it, you get a speaker model. So the UBM of each model is a DMM. Each of them will be represented by a vector of weights, matrix, and a matrix of means and matrix of covariances. So hopefully you understand how the size of the feature vectors here, how we are representing a speaker model using DMMs. Model representations are supervectors. Now you know that DMM can be represented by supervectors. Instead of all these full data, we can come up with a new idea which is called supervectors. Supervectors is formed by a concatenating all individual mixture means scaled by the weights and the covariances. So instead of having mean separate, covariance separate, and weight separate, what we can do is we concatenate all the supervector, all the means and weighted means by covariance, and that would be called one supervector. Now the beauty of the supervector is that there is a fixed length. Whereas if you don't use supervector, then every frame you have to calculate various things. But supervector is an idea where you can hold at utterances, like many frames at the front end level, translated through all this modeling, eventually can give a fixed length of means. That's a fixed vector. So the utterance length could be any length, but feature level wise supervector representation will be a fixed length. So speech of different durations can be represented by supervectors of fixed size. So model normalization is typically carried out on supervectors. So normally when we do model normalization, we do it on supervectors. So this is just, I haven't introduced in more detail this one, which in other slides will later on I'll show you, but I thought I'd just introduce this first to how we represent the big vector by modeling. So all we are saying is that if we go back to it, we are saying we will be only using the mean, and this one will be used to weight the mean, and we will only use that as only mean, and put them all is one length. So 39 by 1024 is our vector fixed number. Detailed speaker verification system. Now we've done speaker modeling. I've explained to you speaker modeling. Earlier we looked at feature normalization, we used feature extraction, and model normalization. Now model normalization is, there are many techniques, NAP available, JFA available, I-vectors, and covariance, within class covariance normalization, linear discriminant analysis, and most recently PLD, probabilistic linear discriminant analysis. So think of in model normalization you have got in the supervector consists of supervectors at that point. That's your fixed one. Here's your variation, a lot of frames like that, and they're all eventually given one full vector through this process. And model normalization is that you take the supervector, which consists of speaker effect and channel effect. Both of them are there. How do you separate them? Or can you suppress the channel effect and keep the speaker effects as importance, give more importance to speaker effect and suppress the channel effect? How do you do it? So think of it in previously you would have probably learned, if you've got two vectors in the same direction, one is a channel vector, one is a speaker vector, you are interested in only on the speaker effect, not on channel. So in that case, you need to find a transform which can rotate slightly this 90 degrees, then you solve the problem, you know. That's the way to think actually. So model normalization, we won't be doing it a lot here because this particular talk will not lend itself, and hopefully we will produce more lectures on this topic alone later on. Now we move on to classification, scoring, score normalization. That's the next part, and you will ask a question, what is score normalization? Think of it, two system, you develop two speaker verification system, and both of them give you output, and the output could be in different ranges. It's same as three graduates coming from various universities using various scoring scheme, and the output may not lie between 0 and one might be 0 and 5 GPA, another one could be 0 and 4, another one could be 0 to 10. So if you have, they're all graduates, but the output is in different ranges, so we need to normalize them to bring them into one range. That's what's called score normalization. You normally need to do them when you are comparing two systems, you know, not otherwise, you know. And then you have the decision-making process. So decision making, how do you do decision making? So what we do is we have a speech here coming in, say this is the person that we are going to claim that he is the person. So it's the claim identity. So that's maybe that's John. So John, we extract the feature for John. We pass it through this one because he is claimed. We know from here John's model is here. So we feed all the parameters from John's model, and then we pass this one also through UBM. And UBM would have generic male model and a female model. Knowing it's male, so we pass it to the male model. And then we calculate a score, which is the likelihood score. So we say log likelihood of S is this one, came from the speaker model, came from here, what's the likelihood? And what's the likelihood of S did not come from the speaker model, that means from the UBM. So you find the ratio, and L is greater than theta, so we set a threshold. If it is greater than theta, we say we will accept. If it's less than theta, we reject. So the claimed identity is accepted if the log likelihood ratio is greater than theta. You need to set up the theta. We need to do a lot of trials and then select a theta value, which comes on the next slides. So that's how you do a decision making based on the log score. Now I come back to score normalization, which I explained earlier. So we are now in score normalization section here. Different system perform speaker verification system in parallel. So this is one speaker verification system using one set of features, which is something different. And maybe another set of features feeds in here and another system there. Because these could be complementary features. And this could be a system, some of these features, but the back end is different. So they all will give you a score 1, score 2, score 3, and these ranges are different ranges and depends on the system. So we need to find a normalization technique. So we need to normalize them. Once they have normalized the score, then we combine them in a particular way, and then we make a decision based on that. So score normalization is very important when you are looking at multiple systems. And it is true when you have many systems, when you combine them, the performance tend to improve a lot, because if you put the features together, they may not be able to separate the speakers better compared to when they are done separately. Yeah. So once you have the scores, the normalized scores, then we use a fusion technique. That means we weight them. We weight that score by W1, we weight that one by W2, we weight this one by Wn, and then we find final score. So you could use a neural network here to do the fusion, and you need to then find the weights using a different set of data, and once you have done that, you could calculate the score. There are many ways of doing it, and so final score will be the weighted sum of each of the system. And that's when you have a multiple system. If you only have a single system, you don't need to do score normalization. You can just from there, you can start at the section I showed you before. Now, performance measure. How do you measure the performance? So concentrate on these two boxes. We say we have a true speaker. Yes, the system made the correct decision. Then it's good. No, the system did not make correct decision because you set your theta, is your threshold high, and it just missed the person. The true speaker is missed. It's okay in an application like access to a room. If a person was missed, there may be another alternative way of getting into the room. So it may not be a major issue. But imposter being accepted is a major issue. Because if theta is low, the person may be accepted, and in a banking situation, you do not want an imposter being accepted, and it's easy enough to lose a lot of money. So we want to make sure that imposter comes in its correct decision. So we want to make sure that the number of occurrence should be 0 here, number of occurrence should be 0 here, then your system is perfect. If ever true speaker comes, it allows you. If the imposter comes, it just makes the characteristic and reject the imposter. That's what we really need, but in reality, that's not the case. And also, we don't know how to set the threshold, so therefore there will be a small amount of error, and setting the threshold is a very tricky thing. And I just show you how you can set it, and depends on, you have to go to work out the application, depends on the application, you set the threshold accordingly. Okay? So let's look at the performance measure, which is using error detection, detection error trade-off curve, which is called DET curve. So basically, we are going to find out how many times this happened, how many times this happened, and we find the probability, and we call it as miss rate percentage or force acceptance percentage. You can have percentage or probability. And we can then, by changing the threshold, theta, we can plot a graph for various theta. If the theta was set up at that position, and then you will find, if you take that as an operating point, here is about 3% miss rate and 0.2% force acceptance. So if you want a banking environment, you want to be on this end. Ideally, we want, force acceptance should be 0. And you will find the theta, I mentioned to you earlier, theta need to be set. And in reality, this curve, each point on the curve corresponds to a different threshold, should be something like this here or here. That's what we prefer. But the system is such that different system provides a different curve. And I'll show you in the next slide how that works. Here's an example. If you have a high security application, this is where you want to be. You don't want an imposter is accepted. So you want to make sure we don't want to be here. So that's a high security application. And if you look at the next one, high convenience. Convenience wise, well, imposter may be accepted. That's not a major. So access to a room, it's not a secure room, but it just has got an access. It's convenience. But if you look at balance, in balance, we want to be here in this region. You don't want high security. Yes, that's the best one. It's convenience or balance. So what we need to have is an equal error rate. So at that point, the error rate, if you take that as your operating point, you will find the error rate is 1%, error rate is 1% for this particular dead curve. What really we would like to see is the dead curve is somewhere there, and you take equal place here, so it's 2%, 2%. So normally what we have is a line going through this, it's called equal error rate line, and that's where we operate normally. So we find the dead curve, then we draw this equal error rate line, y is equal to x, like as an equal error line, and then find where it cuts the graph, and that's our equal error rate. So you will find that that's the line there, and we call these points as equal error rate point. That's an equal error rate point. If you have got another dead curve is somewhere here operating, it's a very good system, then the equal error rate is very small. So more you move this direction, your system moves, is better system. If you move away from here, your system is not really good. So that's how you look at look at your performance of your system. You plot the dead curve and you draw your y equal to x line, and where it cuts tells you the equal error rate. And these are just applications of where you use them. Similarly, an application customize full rejection, alienate customers, and any customization is beneficial. Yeah. Now we come back to how do you do this evaluation? Where do you get the database from? If you're going to implement a system, and there should be a standard database, because people can implement different systems using different database, but then reporting the results, they are not same because they are not in the same condition the data was collected, so there's no common platform. So NIST, Speaker Recognition Evaluation. NIST is a National Institute of Standards and Technology, established in the 90s, and where they provide you database for you to test your speaker recognition system, and and if you participate in NIST every 2 years, I think it happened, and you get the database from them, and then you can submit your system, and then eventually your system is evaluated, and you will know how good your system is. So it's just a NIST evaluation, it's participation. So driving force for advancing the state-of-the-art speaker verification system, the conditions of data was different, different amount of data, 10-second data available, 3 to 5 minutes data available, 8 minutes data available, different channels and channel conditions, and the speakers are English speakers, you've got non-English speakers and multilingual speakers. So the database itself, the one that they've collected, has got variety. So it's, as I said to you, this evaluation started in 1996, I think, and you will see the first SRE series was in 1996, where they called for people to submit their system, and they were evaluated on the data that they provided. And then 2000 they had the first non-English speech data, and then 2001 they introduced cellular data as well for, and then 2005 they had multiple language with the bilingual speakers. 2008 they had interview data, so interviewing people, and 2010 was high-low vocal effort, and also they had human-assisted speaker recognition task as well at the time. So they were both running. 2012 was a very difficult data, which is a broad range test condition with added noise and reverberation as well, and it was very difficult data to try out. So what you do is that you can use some of these data to train your UBM, but for your development set and test set, that need to be the current data that has to be submitted. So if you are interested in participating, you need to register yourself with NIST and participate. That's every 2 years. And you will find that the past database are typically used for UBM and estimate channel compensation parameters. If you want to look at channel compensation parameters with the new system, which I haven't explained here, and you use the past data for it. So that's all a simple system I've explained, but I just want to show you the trends, what has happened in speaker verification system. It started many years ago. Now look at the basic system, which just I have explained to you, which is the feature extraction part, which I explained to you, and I explained to the UBM, how to develop UBM. Using UBM is the GMMs, 1024 in this case, I explained that. And then for speaker modeling, how do you get a speaker model using map adaptation, then how to calculate the log likelihood ratio, how to then calculate the equal error rate, varying the threshold, and how to, and I have explained that to you. That's the basic system of a speaker verification, right? And then and the trends, then look at the trends, what happened. In 2004, they improved the classification part. As I said to you, in a speaker recognition, you've got a front end and a back end. The back end classification part, we started to look at super vectors. So after map adaptation, we have got these 3 parameters comes in by 1024, and then we weighted the means and concatenate all the mean, and weighting was done using these 2, and we had a fixed vector. So it's earlier it's 39 by n feature vector, and then you found that it was 39 by 1024 mixtures. It was a fixed vector. Then they used SVM, support vector machine scoring technique, and that was a system in 2004, 2005. And I think 2005 then the NAP came into play. So for that system, you added on further. The NAP is like it's a projection and technique, and it's basically suppress the along eigenvectors corresponding to the channel effect of a supervector space. So like, you're suppressing the channel effects and leave the speaker effects. So that's what we are interested, not on the channel. Because the channel that channel could be basically you record them in various conditions, but when they are testing it, you could be using a mobile phone, it's going to multiple paths, and that it will have a different channel effect. So it's important to remove the channel effects where possible. So that's a new technique came in 2005. And then 2007, more channel compensation came, which is a joint factor analysis, again, which was represented by hyperparameters, V and U and D matrices. And again, you can see in all cases, you are dealing with the speaker components and the channel components. Always that's what we are interested in, the speaker effects or speaker component. And we used then, using the factor analysis, joint factor analysis, speaker factor people were able to extract speaker factor. And not only the speaker factor, then the dimensionality also is reduced here. And then you use within class covariance normalization. Within the class, you use the covariance normalization technique. That also helped. And then you use SVM scoring. And so these colors tell you the new thing came into the system. Little by little, the system get complicated and complicated and complicated. So, and 2007, then you go 2009, then total variability matrix came into play, which is the I vector. So I vector extraction is here. So I vector extraction is very, very attractive. It's a low dimensionality. It's a low dimensionality I vector used to represent speaker models instead of supervectors. So we remove supervectors. We don't use the supervectors. So supervectors are very long and high dimensionality, whereas the I vectors is a very low dimensionality. And then linear discriminant analysis came into play, and it's like dimensionality reduced by retaining only the most discriminative direction between the speaker models. And it was a very, very attractive technique. And then they used the cosine distance method for scoring, which is like the angle between two vectors, that technique. So estimating similarity between the speaker model based on angle between the I vectors. So so it's angle between vectors is what is the cosine distance method scoring technique. So that was in 2009, I think. Still, then another improvement came into play, which is the PLDA, which is the probabilistic linear discriminant analysis. I vector space is decomposed into speaker and channel models compared to the speaker subspace. So that's another way of improving it. So that's the current trend in 2009, 2010. People are still using PLDA. Then in between you get a deep neural network came into play in many areas here, and people are still working on it. This is the current state-of-the-art system. 2009, 2010 is still PLDA is very popular. That's basically bringing my talk to the end. And I've given you an idea of, a speaker verification system. If you are interested in getting into this research area, and if you want to implement a system, how do you implement a basic system? And then I've shown you some trends and what direction things have taken, and why system got complicated. Database that NIST provided is also very difficult data. The system needs to handle that. So different techniques were developed, and people have been working on this one, and I've given you some idea on that. So now we come back to, the last part is, where are we, what direction we are going now? So, okay, we are developing this system. So in real application, what will happen in 5 years' time. Maybe one example I can give, this is just my thinking, is that currently you take your mobile phone, for example, you've got keypad on the mobile phone, and if you want to lock your phone, you just key in a number 452 8 or something, and the phone get locked. Once it's locked, later on, if you want to unlock it, you type in the number and you unlock them. Now, look at a scenario where you've got a mobile phone, you just left it there, it's unlocked, but you're sitting here with people and you're talking to the people. So the future system should be something, if it detects your voice, the phone remains unlocked. If it does not detect your voice, it just gets locked, simply. That would be a system that I think it will be there. You don't need to use the keypad for locking and unlocking. By listening to your voice, it should be able to unlock. And it's not that far away, the technology is to do that, because but the difficulty is that to implement all the algorithm, then you need to put that in the algorithm need to be in the phone, then power consumption and the size of the phone, whether do the algorithm in the phone or do it on the server. Then if you do it in the server, then can you reliable? The reliability problem comes into play. Quite a lot of other problems are there, but in time, yes, I think that phones will have that identifying your voice basically. And if you are sitting here and if you just move away from here, just left your phone and the system doesn't detect your voice, it doesn't hear your voice, that automatically locks itself. And when you come back and then you're just sitting with people or you're just talking, and it will just detect your voice again, and then it's just unlocks it. So that's an application that you can think of in the future. Or again, if you are interested in working in this area, that's one application. There are many other applications as well. I think this APSIPA distinguished lecture, I've tried to summarize speaker verification. This is meant to be introduction for people, students like you, PhD students who are interested in working in this area, those who are already working in this area, those who are interested in getting into this area. So this is like a summary lecture of speaker verification in an hour. We are hoping that we will record many lectures like that, in the boxes that we showed you through APSIPA. At some stage, we will record, one lectures on each of these boxes, hopefully, or two of them together. And the aim is to create a bank of lectures, hopefully by APSIPA. APSIPA has got the members are good experts in this area, and so APSIPA has set up this distinguished lecture program, and you may be able to look up these lecture programs yourself, and there are quite a few very interesting lectures available, and hopefully that we will build up keep giving these lectures and then record them. All right, thank you for listening to my lectures, and if you have questions, you can come around and ask me or individually, and also I want to thank again the Ho Chi Minh City University Technology for inviting me to provide this APSIPA distinguished lecture. Thank you.